Let's just jump right in. Our entire world, it runs on information, right? You've got signals beaming down from satellites, you've got endless traffic flooding the internet. We are swimming in these massive, seemingly random streams of data. But how? How do we actually make sense of any of it? How do we find the signal and all that noise?
I want you to imagine something. Let's say you're an engineer, and you're trying to figure out a new communication system. The only thing you have is one long, continuous feed of data coming from it. How in the world could you possibly understand the entire system, all its possibilities, its average behaviors, its limits, from just that one chaotic stream? It feels impossible, right? But it turns out there's a really powerful idea that makes it all work.
So, in the world of math and engineering, these chaotic streams have a name: stochastic processes. It's a bit of a fancy term, but all it really means is a system that generates sequences of data over time based on some probability rules. Think of it like a mathematical blueprint for anything that spits out information, whether that's the weather, the stock market, or the data packets zipping through the web.
To even begin to understand these processes, we have to figure out how to measure them. And as it turns out, there are two totally different ways to come at this problem.
This right here breaks down the two perspectives perfectly. First up, you have the time average. This is where you watch one thing for a very, very long time. The analogy here is great. Imagine tasting the same single spoonful of soup over and over and over to really understand its flavor. Then, you have the ensemble average. This is where you look at all possible versions of the system, but just for a single snapshot in time. This is like taking one tiny sip from every possible spoonful of soup, all at the same moment.
So, that's the crucial point, right? We have these two completely different ways of getting information. We can either watch one thing evolve over a long period, or we can see absolutely everything all at once.
And that leads us to the big question. Are these two methods, the time average and the ensemble average, just separate? Are they doomed to give us different answers, like two separate worlds of understanding? Or, and this is the important part, is there a secret connection, a bridge between them?
Well, this is where one of the most foundational ideas in all of information theory comes into play. Yes, we can build a bridge. And that bridge has a name: ergodicity.
Ergodicity is this remarkable principle that for many of the systems we really care about, those two averages, they're exactly the same. If a process is ergodic, it means that watching a single instance of it for long enough tells you everything you need to know about the average behavior of all possible instances combined. The long-term story of one single thing becomes the collective story of everything.
And this idea, it's not just some neat little mental trick. It's a fundamental property that lets us make incredibly reliable predictions. Just like the quote says, a single long observation is enough. That data stream you're watching isn't just a random piece of the puzzle. It literally contains the statistical DNA of the entire system. Now, I know what you might be thinking. This sounds a little too convenient. Maybe just a handy assumption. But it's not wishful thinking at all. It is backed by some seriously rigorous mathematics. The proof is anchored in what's known as the Shannon-McMillan-Breiman theorem. Now don't worry, you don't need to memorize the name. But what you should know is that this is the formal mathematical guarantee that the ergodic bridge is real and reliable, at least when we're talking about information sources. It's a theorem that gives us the confidence that what we see over time truly reflects the whole shebang. So how does it actually work? Well, it's through something called the Asymptotic Equipartition Property, or AEP. It sounds super complex, but the idea behind it is actually pretty simple. Imagine flipping a coin 1,000 times. Sure, getting 1,000 heads in a row is possible, but it's wildly unlikely. The vast majority of outcomes are going to be somewhere around 500 heads and 500 tails. Those are what we call the typical sequences. The AEP proves that for pretty much any data source, as the stream of data gets long enough, it will almost certainly be one of these statistically typical sequences. And all of those typical sequences share a predictable probability. The chaos kind of settles into a pattern.
So what's the bottom line here? The theorem proves that by observing just one long sequence, we can learn the statistical rules of the entire system. That seemingly random flow of data starts to reveal its own secrets, letting us predict its nature without ever having to see every single possibility.
And this is not just abstract math. Oh no. The ergodic bridge is the invisible foundation that's holding up so much of our modern digital world. So why should you care about this? Well, because of ergodicity, we can actually measure and quantify information itself using a concept called entropy.
It's the absolute bedrock for analyzing signals and designing the communication systems we use every single day, from our Wi-Fi to 5G. And remember that predictability of typical sequences we just talked about? That is a core principle behind data compression. When you zip a file, you're basically making a bet that some data patterns are way more likely than others, a direct consequence of this theorem. It's the vital link that turns abstract probability into the tech you hold in your hand.
When you boil it all down, that's what this is all about. Ergodicity is this profound and really practical idea that a single patient observation can unlock the secrets of an entire system. It's how we find the reliable statistical order that's hiding inside an endless stream of chaos.
And that kind of leaves us with a final thought to chew on. If a single flow of data can contain enough information to describe a whole universe of possibilities, what are the data streams in our own lives? In economics, in biology, and society, what are they trying to tell us? If only we were to watch long enough to see the pattern.